Okay, so this talk is called What Can I Do with Deep Learning? My name is Kastner. I'm here from Mount Kisco, like you just heard. Also associated with University de Montreal. Used to be called LISA, now Mila. We are an institute, not a lab. We are growing, growing, growing. Hooray. So I'm going to first show you a whole bunch of stuff that people have done. Some of it you've probably heard of, some of it you probably haven't. And then the last part of my talk will kind of be what I think is an underlying conceptual framework that can start to wrap together, especially some of the recent research in deep learning. And nice. This password, lagging. Very a lot. I'm actually not typing right now. It's kind of incredible. Okay, so now we're back. So, first I'd like to just introduce the automation spectrum. This is not complete. If your package is not on here, I'm very sorry. I included as much as I could, and I'm still running out of space, and I included stuff that's not even Python, because I have to start growing this. On the left-hand side, you can see statistics. Normally what we associate statistics with are very rigorous methods, typically with the goal of introspecting. We want to find underlying, typically causal, or at very least strongly correlated factors to describe something. In science, you see this a lot. I'm studying stars. I want to discover the underlying thing that makes this star different from this star or whatever. In the middle, you have machine learning. I put scikit-learn and Shogun there. There's a bunch of other packages. I'm very biased to work on scikit-learn, like it a lot, think it's amazing, and it covers like a huge range of potential problems to solve. So if you want to just do machine learning generally, definitely check out scikit-learn. Also, scikit-learn, from a developer perspective, has much less pain than anything over here on the right, and I will just say that up front. The tools here on the right are very bleeding edge, very new, and you better be willing to probably bleed a little bit if you want to get onto the research edge of deep learning. So deep learning is primarily concerned with automation. We're not trying to find underlying causes. We're not trying to discover the order of the universe. There's a few neuroscientists who are starting to use deep learning to kind of like reverse backwards and look at the brain and how it processes information, which is interesting, but other than that, there's not a lot of this going on. Generally, we're just trying to solve really hard problems that are easy for people, hard for computers. And I think so far, deep learning has achieved very well in this domain. So the underlying technology, the three of the kind of core things I'm going to talk about are Theano, which is made in the University of Montreal. It is an optimizing compiler that does automatic differentiation. You can run on the GPU or the CPU with a single flag. Note that GPUs are very important for deep learning, and I'll touch on it very briefly, but most of the time, you want to make things go fast. You get a big old GPU that gamers would love, and then you sit in the command line all day. So if you're a gamer, you're gonna have to fight through that any way you can. I used to play a lot of games, so I had a good GPU, and now I just sit in the command line. Caffe is by Berkeley. It's computer vision tools mostly in C++ and CUDA. It also has a Python interface. Some of the demos I'll show are made in that. Very good if you want to do computer vision stuff. Torch, NYU, Facebook, Google is kind of a competitor. It's C and CUDA operations wrapped in Lua, so it's a much lighter overhead to go between the underlying math layer and the stitch it all together layer. And a lot of the research that's been coming out of Facebook and Google's research divisions has been with this. It's also really great. I don't use it as much because I like Theano. I think it does a lot of really great stuff for you that you kind of have to do by hand in either of these other packages. But as long as you can get something going, it doesn't really matter. What's more interesting is the math and the things you're doing underlying it. So first off, scikit-learn-theano is a package I work on and started last summer while I was in France, partly for looking at neuroscience type problems, but also because I only had a MacBook Air and I wanted to do stuff. So this is an example from our website. Basically, you load up a pre-trained network and you say, I want to find dogs and cats, and it spits back all the points in the image that are dogs or cats. So it localizes dogs and cats in the image. Generally, anything that is in something called the WordNet hierarchy that you can look up is a valid string. So this is a great way if you just want to like cram in some images and look at them. It works really well. If you're used to the scikit-learn API, you'll notice there's no fit because you cannot fit. Sorry, you predict. That's it. This is like a very minimal framework. It gives you very specific tools to do one thing. It runs on the CPU or the GPU. It's pretty fun to mess around with. Done with the self-plug. So if you do more image processing, Lasagna is another package for this. It has been used extensively in Kaggle competitions by a former PhD student of University of Ghent, who's now at DeepMind, which is like Google's neural net research arm, or one of many of their research arms. It's more of an octopus at this point. They won 2 competitions on recognizing plankton at galaxies. Structured like an image. 2 blogs and kind of say, oh wow, that's a really smart way to think about my problem. Like I said, they won some competitions with it. The thing at the bottom is a learned transform and manipulate images so they could get a better score. They didn't end up using it in their final rotations and transformations and stuff, because one of the things you usually have to do is warp the images around and make it look like you have more data than you really do. But people are trying to put that into the network as well. So Caffe is kind of the workhorse of deep learning for computer vision. It's used in both research and industry a lot. It's kind of a beast at computer vision. Most of the neural network type stuff is going to have pre-trained stuff done for you so you can just run it. It requires some install. It's a little more overhead to work with, but in the end, it's very good at the thing it does. There's lots of unique tools. What we're seeing on the right here is a toolbox made by my friend Jason Yosinski. And inspect them. Looking at it. His research is trying to open up the black box and figure out how they work. So you I encourage you to check it out. Detector. So innate in the processing of whatever is the ability to detect faces. And it's just learned naturally from data. Lots and lots of data, but still learned from data. Very interesting, very cool stuff. We can also do generative models of images. So what you're seeing on the right is something called the Directed Recurrent Attention Writer, DRAW. And it learns to draw that are like, try it, you can just run it. It's in Theano. Generative models of images. So what you're seeing on the bottom right is an NYU production slash the technical name is Laplacian conditional. If that means something to you, good job. For me, I think ice cream's kind of a cool in the references section. Easy, there's not a lot of planning. Go find the ball, make sure it doesn't go, and that's it. There's more advanced games, and DeepMind especially is working a lot on planning and kind of long-term reward, things like puzzle games and things like this. And so this is kind of a very interesting line of work. Once again, this code is in Torch. You can download it, run it yourself, and see what you think. Try to plug in other games, try to do other things. It's all right there.
But none of this stuff has yet made it into chess engines.
So the question was, none of this stuff has yet made it into chess engines. So there's a thing that I didn't put in my slides called convolutional neural networks learning to play Go. So they're starting to use these in Go a lot. One of the big problems is, once again, planning. So if you choose the greedy move, a lot of times you don't end up with the best overall result. But there is a lot of research in this area as well. So once they figure out how to do it, I'm sure we'll see a publication. But right now, like Sunfish and these other kind of advanced handcrafted engines are very good because people spend a long time working on it. But the goal is, hopefully in the next year or two, we can kind of take over 20 years of research with two. And that's kind of the story with all of this stuff. A lot of very smart people have worked for a really long time on really hard problems. And so you're not going to overcome that overnight. It's not magic, but it is cool. All right, so you can also win competitions on heterogeneous data. Up till now, we've talked about images. And some of you might be saying, boring. I don't care about images. I care about audio. I care about something else. turns out neural networks are good for general processing of tasks and for encoding domain knowledge. Once again, there's a great write-up on how these guys won the competition. It kind of shows how you can structure a neural network to encode the things that you know about the problem and predict something. So the goal in this was given the first couple GPS points, a time, a taxi ID, a client ID, some other metadata, predict where the taxi's going. And they did very, very, very well and they ended up winning the competition. They're students and interns at the University of Montreal. Our lab is big enough, I had no idea they were doing this. I talked to them a lot. There's like 60 of us or something now. And I left for IBM and they won the whole thing. So definitely check out their write-up. But you can use neural networks to make decisions from heterogeneous data as well. Things like databases, things like strings and text, which I'll talk about a little bit. It's good for more stuff than just images and audio and video, if you're into this kind of stuff. So now I'm going to lead into the back half of my talk, and I think I'm running a little low on time, so I'll go fast. Text-to-text translation. There's some demos of this around in blocks. It's something called a recurrent neural network and an attention mechanism. I'll talk more about this later. But basically, you can take very large parallel corpora, basically English and French, or Spanish and English, or French and Spanish, or whatever. Like the UN has really great data sets for this because it's automatically translated to all the European languages. German is actually not as good as the rest right now because it's got different structures, but they're working on it. So basically, you feed it pairs of sentences, train it for a really long time, and it learns to translate one to the other. And this is actually a web demo. So if you want to Google neural machine translation, you will get a website that is actually an IP address. It doesn't have a DNS. Don't be scared. That's actually the demo. And you can type in sentences and see how the translation comes if you're bilingual. I'm actually not bilingual at all, which we talked about before. So I actually can't evaluate how good the translation is. But I am hopeful that this will kind of take over and maybe keep me from having to become like fluent in French. Maybe I could just be moderate and succeed in Montreal. And the French speakers of Quebec would not be happy with that sentence. You can also do handwriting generation. So a very similar framework can also be used to generate from text handwritten characters like captured from a whiteboard from a bunch of teachers. Once again, there's a web demo of this by Alex Graves, formerly Toronto, now at DeepMind, doing stuff like the Atari game. So he's putting his brain and skills to good use there. And basically you can generate handwriting in varying styles and with varying levels of influence, and you can actually use it to clean up existing handwriting and a bunch of really interesting stuff. The paper is basically a how-to on sequence generation, so including things like speech. The technical details are basically you have a mechanism that at every time step spits out the parameters of a Gaussian mixture and a Bernoulli distribution, and then you sample from that. And at every single time step, it's doing enough to know the dynamics and the structure of handwriting from raw information. So once again, really cool, kind of complicated. There's a write-up. Urge you to check it out if you're into like speech or handwriting synthesis. So there's also a task that was proposed in a recent paper called Towards AI Complete Question Answering by Weston et al. From Facebook Research. There's also a recreation of this in Keras, which is a Theano-based Python library. The core code is there on the left. Basically, two sequence models that cram together and feed data to another sequence model, and I'll show that in just a minute. But it's given like a series of actions and questions from a limited vocabulary, and it actually learns to generalize this and figure out where the ball went. And this set of tasks is actually being learned to create general computational models that I'll talk about a little bit. There's actually something called the neural Turing machine, which is a neural network-based Turing machine. There are neural network-based stacks and queues and DQs and all these kind of like computer science things. I studied electrical engineering, so I'm very mystified by all of that. But the neural Turing machine has a memory, and I get that. So people are working a lot on these types of problems because once again, like a series of questions and answers or a series of actions followed by a query this is like a smarter search engine. Don't write your own search engine, but if you're gonna write one, you better make it smarter than what's already there. And so Google and Facebook are working on these kinds of tasks right now. Okay, so now we get into the technical portion, and I'll come back to the baby RNN and some other stuff. I've got 10 minutes, 8 minutes it looks like, so this is going to be a whirlwind. And my blue text doesn't show up. That's a bummer. Basically, that says the probability of y given x1 through xn, comma, label 1 through label n is what we're trying to predict when we do conditional modeling. So what this actually means is if you have a neural network that has a set of weights, and you have a neural network that has another set of weights, you can actually just take the inputs, concatenate them together, make one big set of weights, make it deep, so make like a couple layers, and eventually what you'll get out at the other end with at least a classifier is the probability related to the joint probability of the input. So if you're used to things like naive Bayes or whatever, they make independence assumptions across features. Neural nets do not make that assumption. This is one of the reasons that they're so powerful. They model general joint probability distributions. The things you concatenate with can also be real valued. Use it to mix, blah, blah, blah. This slide has no images. I'm so bored right now. Latent factor generative models. So this is another thing that's come up recently. There used to be something called the Auto-Encoder a long time ago that people are still working on and was generally very exciting because it was unsupervised. You didn't need labels. Labels are expensive. Labels come from people. We don't want labels. We want to learn about data from data. We want to sample from a microphone and learn what speech sounds like. We want to look at video and figure out what video is. We want to look at space and figure out what space is. We don't want to have astronomers who are very expensive, or relatively expensive if you ask them, come in and label stars and tell us what to do. So labels are expensive. The farther away you can get from labels, the more data you can get. Sadly, that data is noisy and it's hard to deal with. So there's a series of papers that I'm very interested in, and my current research work is all in, that basically takes this autoencoder structure that says, take some data, compress it, and then learn to uncompress it. And in that compressed representation, you've learned something about the data itself. What that is kind of hard to inspect, but you've learned to compress. And so this is actually really interesting. And what you see here is going into the compressed space and saying, generate me things that are close together. And you can see if you walk from left to right, 6s become 0s, become 2s, become 1s, become 9s, and it learns something called a smooth manifold between digits. I can't go into too much detail about this because we're running out of time, but what it means is it's learning a relationship between these types of classes. So it's easy to see that if you wanted to separate 1 and 9, this general task of learning the relationship between the types of input could be really useful. This is the actual structure of what it looks like. So I won't go into much more detail, but in general, when I'm talking about weights, the weights are all the directed lines in the middle, and what we call neurons are the little circles. So this is actually a really small network, but it is deep because it has 4 layers. It has 2 on the input, 2 on the output. It's deep. It has like 20 neurons. We're deep learning. Ooh, not quite. Most of the networks I've shown you up to now are like millions to like multi-millions of neurons, so like a really big version of this. So if we visually look at what conditioning can actually do, if what we have on the left is just walking around in this space that I'll call Z and looking at neighbors. So you can see you learn smooth transitions between digits. I have a web demo of this, but it's not posted in the references. I'll do that before I put the slides up. On the right, you see what happens when you walk around in this Z, but you have a control, you have a Y, and you flip it. And that's what you're seeing in the bottom left. And so what it means is you can walk anywhere around in Z, and then when you say, I'm tired of what you're doing, I want you to become a 3 or a 4 or an 8, you can flip that and you have control. And this is very interesting from a synthesis perspective because unconditional generation is boring. We actually have a model that does unconditional generation of speech, and it's basically like, which is completely not useful. No one will use a Siri that goes, no one will do that, right? So we want to add conditioning, but it takes work to get there. But the general idea of conditioning is this. We have sight information. We know that the style of the way a digit's written and what it is are different. So when we build the network structure on the right, we're saying, learn to separate these. And it actually does. So what we see on the bottom here is on the left is the original input. On the right is the same z for every input, flipping y between all the classes. So you can actually see that, like across the second row, it's learned that there's some slanty, scribbly style, and that's consistent across all of its generations when you flip through the classes. For the fourth row, or the third row, if you zero index, the blurry version, it's holding the blurry style fixed. So if you extrapolate this to speech, like we're hopefully trying to do eventually, you could imagine learning things like accent, things like gender, very natural things about complex data. We're a long way from that, but we're getting there. Recurrent neural network. I have 2 minutes. So long story short, the states of a recurrent neural network, S of t right there, do something that models the joint probability of a sequence. This is very important if you want to do translation, because the joint probability of the English sentence relates to the joint probability of the French sentence you're going to generate. Once again, you can condition it by whatever you start the network with, saying this information is what you need to start with. So if you have an English sentence, taking a compressed representation of this and starting the network with it, then saying generate me French is a good thing. You can also do conditioning in the feedforward layers, which are at the top and at the bottom. And so you can condition all over the place. And this is how the English to French network actually does its thing. The baby RNN, yeah, there's no way I'm going to get through this. Basically, if you look at the slides, we're modeling the probability of a story as the joint probability of all the words using a neural network. And then we're modeling the probability of the question as being the probability of all the words, once again. Then we take those, concatenate them together, just like we talked about for feedforward, and then what we get out is the probability of the output given the joint probability of the story and the query. And so this is one simple way to solve that really complex problem. And you can see we're putting the structure of our data into the network, not into the features. Yeah. Bidirectional recurrent neural networks. This is used for speech recognition. And long story short is attention and memory are basically the same thing. It's different ways of differentiating what you're looking at and where it's stored. And there's a bunch of research going on in this direction, including differentiable data structures like stacks and queues and so forth. Here on the right, we see correct and incorrect attention. So up at the top, you're given an input image and told learn to generate captions from that image. So the network actually generated the caption, a giraffe standing in the forest with trees in the background, given a raw image. And when we look at the attention that it's paying in the image, we see that it's actually learned from raw data what a giraffe is and especially what it isn't. It's looking at the trees behind it and not the giraffe itself. And we can also inspect the attention to figure out what it's getting wrong. In this case, a woman holding a clock in her hand is not the correct caption. But we can see that it's focused on the emblem on her shirt, which, you know, if you've seen enough images of Flavor Flav or something, you might actually think that that's a clock. It's a reasonable mistake. So once again, this is another way to take very complex, very complicated models and inspect why and how they're wrong and try to correct them. If we know it's messing up this clock thing, maybe we will find many more examples, or we'll fix the caption on this image to say this is not a clock, and then go forward with our training. If you don't want to install or train any of this, there's a lot of companies who are providing this behind a nice, clean API. So you just send images, or you send text, or you do whatever, and they send you back answers. So you can still use the power of this deep learning stuff without installing it, without getting into the big nasty headache of all the papers that I spend all my time reading. If you don't want to do that, you can outsource the problem. And so these companies, and I'm sure there's many more, are doing this. So that's the end of my talk. Twitter and GitHub, and the repo is there, and the slides will be uploaded to SpeakerDeck and in my repo. Thank you.